parameters or optimizing the functional forms and so on. So I will go through that. Sometime back I was discussing, let me share my screen. Sometime back I was discussing about the radar data. So let me go. Can you see my screen now?
Yes, sir.
Okay, so this is the current radar map of United States. This is powered by the National Weather Service. So as you can see, there is some rain in the northeastern part and the middle of US, and then of course on the northeast again. So the colors of the rain reflectivities are color coded. So you can see that this red color here is anywhere from 50 to 60 dBz. So central value, if you take, will be 55 dBz. So the yellow parts are much lower and the green parts are much lower. So these are the reflectivities which the National Weather Service provides us through the process of sharing to the public. And of course, this is a visual representation of your reflectivities. So, and this value right now can be converted into a rainfall. So for example, let me use my notes here. I'm going to start my notes so that I can write it on that. So typically what we do is we take the reflectivity value and then we apply a power relationship. If you have calculators handy, you should be able to do some number crunching for that. Okay, so let me use my whiteboard here. So for example, the Z reflectivity is given by a relationship AR to the power B. So this is our relationship. Now Z is the reflectivity. So, and R is the one which has units. This is millimeters per hour. Okay, reflectivity, as it is electromagnetic, what you call units, it comes as a very large unit, and it is kind of embedded into the equation. So we get in the form of what we call dBz, that is decibels of reflectivity. So dBz is the one which we get it from our radar centers. So in future, when you have the radar data available to you, they will also be available in the form of dBz, that is decibels of reflectivity. So what is decibels of reflectivity? This is basically n log n z. So this is your 10 times log 10 to z is your decibels of reflectivity. Now, as I told you in my presentation, the A and B values are region specific. So you can use different values depending upon where you are located. For example, a tropical relationship for most of the time in regions will work as A is equal to 300 and B is equal to 1.6. Of course, there are variants of different relationships we can use, and sometimes those relationships are not sacrosanct. That means you have to go back and come up with new values for A and B. So, but typically we start with 300 and 1.6. This is, or 1.4, sorry. So typically we start with 300 and 1.4. This is our standard A and B parameters. And it generally works very well for the entire US. But of course, some portions of US might have different values. As you can see, I showed you numbers for different parts of the world. Even there's a site where Chennai also has a number, or the 2-parameter number. and then also different values can be used. So based on what I have just shown you from the National Weather Service radar website, so these parts are red, indicating that they are currently experiencing heavy rainfall. So that is 50 to 60 dBz. Just the color doesn't mean that this extreme rainfall, but it's a high level of reflectivity what we are seeing. So that means our dBz value is 55. So once you have that, then probably we can plug it in. So 10 log 10z is equal to 55. So then 10 log 10z, log 10z is equal to 55 divided by 10. And then finally, we are left with z is equal to 10 to the power 5.5. So that should be fine for everyone. Okay. So if you're okay with whatever I'm writing, if one of you can say yes, so that I know that there's a confirmation that you're okay with what I'm writing. Or if you have any questions, you can say no, and then
yes, sir. Yes,
sir.
Write.
Yeah. So that would be better. I mean, that way I don't have to worry about, the chat is okay. Chat I can check, but so this is my z value. So that means in the next step I can put 10 5.5 is equal to 300 r to the power 1.4, and r to the power 1.4 is equal to 10 divided by 300. And if we want to calculate the r value, obviously 10.5 divided by 300 to the power 1.4. So if somebody has a calculator, maybe quickly can provide that number, what that would be in millimeters per hour. So that's the amount of rainfall approximately that is falling right now. Of course, this is given in the form of intensities. So if you were to multiply by 6 minutes or 7 minutes, depending upon how much time the radar will take to complete one rotation before the reflectivity value changes, you can actually calculate the amount of rainfall that is available. So any calculations anyone can provide quickly, or should I calculate using Excel? Or please let me know. So this can be a little more interactive. Otherwise, I can always leave it there, but I just want to make sure that you.
There are 2 answers in chat box, sir.
So there are. Is there any answer which came in the chat? Not sure. Not checking the chat. Let me check.
144 mm, and other answer is 144.27 mm.
That is fine. So 144 mm. So that basically tells us that that's the millimeters of rain that is coming down right now at that particular location, millimeters per hour. So typically these values are obtained, and then what we do is we go ahead and do the bias correction. So basically the antenna looks like this, and then it sends out the electromagnetic signals, and on the top of that, that's what we call the radome. It's like an enclosure in which the radar is located, and then most of the time the antenna is listening to the electromagnetic signals, so it only takes 7 minutes to complete the rotation. So once it completes that, the rest of the time it is looking at the reflectivity values, and then they are processed, and then the actual Z values are provided and recorded. Of course, there are a number of processing steps we'll take here. The first one is to remove any background clutter or background reflectivity, for example, if you have a set of buildings and mountains or any other obstacles from which reflectivity is coming back, you have to first subtract. So what they do is they take the signal or the reflectivities on a clear air mode. That means there's no rain. In that case, they get all the background reflectivities. So next time when they get the signal, what they do is they remove the background noise, and then what we have is typically the z value. Now these z values are provided to us in the form of a polar grid. So typically this is what happens in US. So and this is the radar location, and then you get values for each of them, and then we take those values for further processing. The only issue is that this polar grid is not constant, so that means every time whenever the radar is making the sweep of the 360 degrees, the polar grid is not constant. So what happens is that creates a problem for us, because we might have some rain gauges which fall in this particular grid at time equals t equals 1, and then at t equals 2 in the second time interval, they may fall into the second grid. So this is a possibility, or some other grid for that matter. So therefore, the co-location of the grid as well as the rain gauge is important for us, because we need to first of all do the comparative evaluation. So that means when we get the rain gauge observations RO, then we have the radar-based, let me call it as RCAP, the radar-based observations. And what we do is we compare both of them. And if there are substantial issues between those two numbers, what we do is we try to see if any bias correction can be made then and then, because we already have the rain gauges. So that is what we do. But of course, rain gauges, if you have a recording rain gauge, you might have a rainfall available instantaneously, in the sense they are not available at regular intervals. So you need to sum them up to get to a particular interval. And then you have to do the same thing with respect to the radar also. So what radar does is, radar will provide you a set of reflectivity values, Z1, Z2, Z3, Z4, Z5. Let's say this is your 15-minute period. So you'll have reflectivity, no reflectivity, and reflectivity. So in that case, we have to calculate the rainfall intensity in each of these individual time intervals, and you have to calculate the rainfall intensity in each of these time intervals, convert them into depths, and then add them to get the 15-minute depths. Once we have that, then we can compare the rain gauge versus radar precipitation. Now, we can do this for a longer period of time, where we have all the rain gauge values and then radar values. Then we go ahead and go through the whole idea of bias correction. Because bias correction, as I have indicated, that sometimes because of the instrumental errors or systematic errors, maybe the radar is on an average overestimating the rainfall or underestimating the rainfall. So that one can happen over the entire region, or it can happen over the a particular small area. So in that case, the bias corrections can be applied locally or globally. So the polar coordinate system, of course, we cannot do anything in the polar coordinate system when we are trying to overlay on top of our GIS coverages. So what we do is we try to convert that into a Cartesian grid, so that we can overlay on top of our watersheds, so that we can do the calculations for either rainfall values or average rainfall values or extremes and so on. We can always do that. So that's the whole idea of radar-based precipitation estimation. Some of the steps I have shown are trying to do that. But of course, I didn't elaborate more on the mean field bias corrections, which is not very difficult. So if you have these observed and estimated by radar values available for different time intervals, so you do gauge over radar ratio. So over this ratio, you can get all of them, and then once you get them, then this will be either sometimes more than 1 or less than 1. If it is 0, that means if the radar is indicating 0, of course, we cannot do those calculations. We have to abandon that particular calculation. And then once we have the ratios, either you can sum them up and take an average. And then once you have the summation, you can always calculate the mean field bias, that is MFB, mean field bias. And then what we do is we multiply every radar value with that ratio so that the radar values will get corrected. That is one form of correction. And now, when I say mean field bias, you're applying to the entire region. Whereas if you're saying local bias correction, so what we do is based on these are the centers of the radar grids, assuming that the data is transformed already into Cartesian grid, then you might have a rain gauge here, you might have a rain gauge here, you might have a rain gauge here. So for correcting this, you can use this, and this rain gauge, and then use either one of the interpolation methods or trying to use simple distance-based inverse distance weighing method to get the correction factors. And once you get the correction factors, you can correct the values of the radar data at that particular location. So that's one of the ways we do the local bias correction. The other way of correcting the local values is that by what we call the quantile-based correction. So you can also do quantile-based correction in the sense that you get the CDF, that is cumulative distribution function plot of your rain gauge data, and then you go through the process of getting the appropriate probability value for the radar also, and then you go back and then get the approximate value from the CDF so that you can actually correct the radar values by what you do. Yes.
In this, when we are doing calculations and considering the rain gauge data, so is it that we always believe that the rain gauge measurements are accurate?
That is a very important question. Yes, we have to go through a little bit of quality assurance and quality control of your rain gauge data. So what is important is that you need to have reliable rain gauge data. Otherwise, bias corrections will be in error. So rain gauge data also might have some level of error, systematic as well as random errors. There can be anomalies, there can be outliers. So the first order of business is to make sure that you eliminate some rain gauges which have problems. Take only those rain gauges which you can work with, which are reliable and nicely maintained. For example, rain gauges at airports, rain gauges at main known locations, which are regularly monitored and where we have some kind of confidence in that. So as you can see that, I hope I answered your question.
Yes, sir. Yes, sir.
Yeah. So what happens is that typically water management agencies in the United States, what they do is they don't do the processing of the radar data, even though they use radar data, for example, for many flash flood forecasting models, for stream flow forecasting models, for rainfall thresholds, to provide warnings to citizens, and so on. So what they do is they hire a data processing vendor, somebody who is well-versed in meteorological data analysis, or somebody who's doing a radar work. So they hire that person, and that person will take the reflectivity values, and then they also do what we call QA/QC of the rain gauges. So that means they they do a thorough check of all the rain gauges, and then finally come to a conclusion that there are some useful rain gauges which can be used over a period of time, and some are not useful. So therefore, we produce what we call 3 types of products, especially the water management agencies. One is the NRP, the near real time. Then the other one is the end of the day. Then there is the end of the month. So 3 products are generally provided by the data vendors. So near real time is basically a quick conversion of the reflectivity values to rainfall values, and that is done by the data provider or data vendor, and those values are immediately transferred to the water management agencies so that they can make quick decisions. For them, this is mostly threshold based analysis, in the sense if the rainfall amount is more than a certain amount, they can start giving warnings. So for example, in Florida, we have, let's say, we have a lot of canals in Florida where we drain water into the ocean. And if the rain gauges are further apart like this, then a heavy thunderstorm, which we are prone to heavy thunderstorm, a cell in this area will not be captured by this rain gauge, will not be captured by this rain gauge and this rain gauge. So this is a very localized thunderstorm that might create a tremendous amount of rain, and that, if it is not registered by the rain gauges, that not help us in providing warnings, because this canal will be flooded. And when this is flooded, we need to make sure that this information is provided to the people who are living in that area. So therefore, the radar data immediately based on NRT, that is near real-time data, just gives a qualitative assessment. Of course, it gives you numbers that at that time, the QA/QC of the rain gauges, some reliable rain gauges must be used, and so on. That process is not done at that time. So the next step is at the end of the day, the vendor collects all the rain gauge data, checks for consistencies, checks for any problems, check for anomalies, check for physical values, check for reference gauge values, and so on. It does all kinds of anomaly detections and outlier detections. And then they eliminate some of the rain gauges. For example, in this case, if we are using 200 rain gauges here, maybe we are only using 150 rain gauges in that region to develop what we call end of the month, end of the day, and then probably only 120 very reliable gauges for end of the month. So these are the 3 products which can be used. The first one is only for operations, emergency operations. The second one is a reasonably good product for a little bit of short-term forecast. For example, there might be a flooding tomorrow or something like that. And the third one is the more final product, which can be used for hydrologic modeling and other inputs to the distributed simulation models they have, a large-scale regional simulations model they have, and also for National Weather Service forecasting models or regional forecasting models, which can take this information. So again, a thorough check of this one and this one with the rain gauge or ground truth will be done. Then only they will accept. Then only they will accept those data sets for the next level of processing. So, any questions on that about the processing of the radar data? Yeah.
Sir, one question is, which precipitation data is more reliable, rain gauge or radar data? One participant has asked.
Okay. First of all, rain gauge data has let me see if I can see the question properly. I don't know. Am I still there? Right. How do I think I minimized it, but I want to go back. Okay, so you can hear me, right? Hello?
Yes, sir. Yes, sir.
Yeah,
Yes, sir.
okay. So the important question is that the radars now, what we are using are referred to as a dual polarization radars. Dual polarization radars are which measure the reflectivity in both vertical and horizontal directions. So that gives them a very good accuracy in terms of actually distinguishing between a fly and a raindrop. Now, because raindrop, when it's falling from the atmosphere, it has some kind of a compressed spherical shape. It's not completely spherical. So because of the air resistance, so the new radars can have a very good, I would say, very good accuracy, where they can produce a good correlation coefficient of a value of 0.7 or zero point 0.8, even without just applying the basic relationship 300 r to the power 1.4. So if reflectivity values are available from any of your radar sites, you can just try this relationship and see how well the radar data simulates the rainfall or estimates the rainfall compared to a rain gauge. Now, for the question whether radar rain gauge data is better or radar data is better, it depends on the analysis what you are looking for. So, for example, if this is your watershed, and if you have 3 rain gauges, there is a very good possibility that the 3 rain gauges might miss an extreme rainfall event because of the nature of the rainfall. If it is a frontal rainfall system which is going slowly, then all the 3 rain gauges will pick up the rainfall amount. But if it is a convective cell, which is a localized thunderstorm or heavy rainfall event, and if you don't have enough rain gauges, they will miss that event. Whereas radar, which basically, I'm putting a Cartesian grid here, is actually getting rainfall in every single grid of this particular on top of the watershed. So therefore, radar data is essentially extremely beneficial for distributed hydrologic modeling. First of all, radar data captures extremes which were missed by rain gauges. Radar data provides spatial variability of the rainfall, which cannot be provided by rain gauges because rain gauges are point measurements. Rain gauges sometimes miss extreme values because rain gauges might malfunction in case of extreme winds or extreme rainfall. So there's a possibility that the rain gauge is knocked out because of extreme rainfall events. So we might miss extremes also in that case. And the other issue is that studies have shown that radar data is much suitable for flash flood forecasting as well as flood forecasting because the spatial variability in a basin or a catchment or a watershed can be better captured than a rain gauge, where you can, for example, if you have a 3 rain gauges in a watershed, you can quickly develop decent polygons and then obtain average values in these 3 areas by area distribution. But then that will not be exactly same as a gridded data what you are getting from radar. So at any level, radar data which is checked with the ground truth and a minimum bias correction, there can be a mean field bias correction if it is done, then you are in a good shape to use that for hydrologic modeling purposes. And most of the flash flood forecasting models, especially in different parts of the United States and the world, they use some kind of gridded rainfall product. In US, we use S-band radars. They have strong strength, and they will have a range of 230 kilometers. So because of their strength, the attenuation, the reduction in the strength of the signal is less. But again, as you go further and further from the radar site, your accuracy might be affected. So therefore, we use multiple radars where there is an overlap. For example, this is one radar site and this is another radar site. So this is the nature of the overlap. So we use the overlap to benefit from having two sources of information confirming either a rainfall event or non-rainfall event. So that really helps us to improve that. So in case of urban rainfall, the urban rainfall is not based on S-band radars in many countries. They use X-band or C-band. These are smaller wavelength radars. They can be installed on top of a building. And the advantage with that is their strength is smaller, their range is smaller, but they are very accurate and on top of a building, or sometimes you can even put it on top of a car and then try to get rainfall very quickly, especially in urban settings, because the rainfall amounts, even though they are known approximately, that rainfall amount can be fed into a simple model, a simple runoff model or a conceptual model, and then you can get your runoff because most of the urban areas are impervious, so they generate tremendous amount of runoff. So that can be used for flooding in urban areas. So those are X-band, C-band radars, whereas in the United States, most of the publicly owned radars are S-band radars, which have a longer length, wavelength, and then longer range. So just to summarize as a final thought, if you are looking for a distributed rainfall input, a gridded rainfall input for your distributed rainfall, hydrologic simulation models, you are better off having a radar-based rainfall product than rain gauge-based gridded product. So because rain gauges are very sparse, we don't have a lot of rain gauges, and they try to mute the variability because of the averages we calculate and so on. Even if you do kriging or even if you do very good geostatistical methods, the problem is that we mute the signal, we reduce the variance. So in that process, your distributed hydrologic models may not work very well. Now, having said that, you might say, well, a lot of countries are still using rain gauges. They are able to succeed in developing flood forecasting models. Yes, you can still do that, but the adjustment happens in the calibration. So now the calibration is overtaking the issues related to the rainfall values which are provided spatially within a distributed hydrologic model. So you are taking the lumped input and converting into a distributed input. For example, if you have, this is this 3 rain gauges, you are using decent polygon or some kind of a surface to generate a kind of a lumped input from, a distributed input from these 3 rain gauges. And the other one is coming from a polar grid, which is converted into a Cartesian grid and bias corrected with the ground truth. So I would definitely prefer the radar product for if it is available in your region. I would prefer that one for distributed hydrologic models compared to a lump-based, rain gauge-based calculations for the distributed hydrologic model. So I know it's a long answer, but I just want to convey the problems associated with both type of data sets. Yeah.
Sir, here I have 2 questions. Number 1, that when there is a storm, will it not happen that the radar measurement will get affected because of it?
If there is a storm, if the storm is there, radar measurement will be
which have higher intensities, whether the radar measurements get affected by it, like the point rain gauge sometimes misses to catch such extreme events correctly. Will it be captured by radar?
Yeah, any type of rainfall event will be captured by the radar because radar is sitting somewhere else. It is not affected by the rainfall region. For example, you can sit 100 kilometers away from the rain region, and then you can still capture the reflectivity. The more the reflectivity indicates that there is more rain happening there. So yes, there is no problem in, for example, we can also know the movement of the storm. So for example, here the storm is moving in that direction. So there's a heavy rain here, there's a heavy rain here. So these, when compared to rain gauges which are there in that region, they will register very well. They will be ground truth. With ground truth, they will be very well. So
got it, sir. Got it. And the second question is, when we are using radar data, it may be available for seconds and minutes. So when we want to apply it to distributed hydrological model, what should be the time scale of the rainfall one need to use?
It depends on your time. As I said, for example, radar data is available in intensity. So typically, as I said, reflectivity is Z1, Z2, Z3, Z4, and Z5. So if this is your 15-minute interval, typically we run distributed hydrologic models anywhere from 15 minutes to 1 hour. 15 minutes is a very fine resolution. It takes a lot of computational resources. But again, if you want at that resolution to give warnings to people, maybe 15 minutes you can work. And then these Z values can have different lengths. For example, the first one is only 6 minutes. Second one is 2 minutes. Third one is 3 minutes. 1 minute, and so this will be 12, and the last can be 3 minutes. So now what we are looking at is that each one, we convert it into millimeters per hour multiplied by 6/60 will give us the depth here. And similarly, we do the same thing, 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 and then we add up all these values to get the 15-minute total. So that's your 15-minute total. And once you have the 15-minute totals, then you can compare with the rain gauges to see how good they are quickly. And then that 15-minute totals can be put it in your distributed hydrologic model. So it all depends on the temporal scale at which you are running your distributed hydrologic model. And then the radar reflectivity values are not, the time frame of each reflectivity value is not constant. Sometimes the antenna spends more time if there's more rain, so it takes more time to complete one rotation. So therefore, sometimes you will have the same reflectivity value for 6 minutes, or you can have for 8 minutes also, or 7 minutes. Typically, it varies between 5 to 8 minutes, depending upon how much the complete 360 rotation takes place. So if you see a radar is not just going, let's say, for example, it starts from here, it goes, checks here, and then it lifts the antenna, it checks for the next level, it checks the next level. So there are multiple levels at which the atmosphere is sampled. That means you have a whole volume of the atmosphere which is sampled. And then it takes the next transition, multiple degrees, and comes back to the original site. So that means that it just rotates 360 degrees, but at the same time, it does multiple vertical measurements. So you will have some discrepancies. Sometimes you'll get for 7 minutes, 5 minutes, 3 minutes, but you have to club it together so that you'll have that total of 15 minutes or 1 hour, depending upon your application. Okay, good.
Okay, sir. Okay.
Yeah. So there are systems. For example, there's a system in Texas. It's called Alert. So what they do is the Texas downtown Houston city, that's one of the major cities in Texas, and then this gets flooded every year with the tropical storms. The problem is, like the cities like in Chennai and Bombay, when they have too much rain, and the stormwater management system cannot handle that much amount of rain, and that creates a tremendous amount of runoff in small amount of time. And Houston has a huge impervious area, and there are lots of underground parking lots, underground hospital wards, and so on in the downtown. This rain completely runs off and then and floods these places. So definitely they need a flash flood forecasting system. So they use radar. They start from the upstream of that particular city for the streams. They start upstream. They have rain gauges and radars checking for the rainfall amounts. They run through a simple HEC-RAS model. First run through HEC-HMS, and then they run through HEC-RAS. Once they finish that, they have immediate stage projections at different levels in the city, and then they can start providing color-coded signals. I think it's called the alert system, and that has a website which will give a color-coded system. So at any given time, the United States Geological Survey will tell you which of these sites are experiencing flooding. So there will be a color-coded, I think, water data. Let me show you data.usgs.gov. These are the people who maintain the water data for us. And then you can see here, there should be current conditions if you go there. And you can quickly see which of these sites are experiencing, high values of stream flow, and then which are crossing 90th percentile. So you can see that at this location where we are seeing in Indiana, and which we can see from our National Weather Service map also, the central portion, especially this area. And you can see there's a heavy rain going on in that particular portion. So that really helps them to do that monitoring and then provide those color codings to the people, indicating which of these rivers are experiencing high flood conditions, which are crossing their 90th percentile or high values. So this also gives a advantage for the public to see what is going on. And this is updated recently, so it's 9:30 in the morning. Right now it's 10 a.m. in East Coast. So June 13th today, they are updated. And that's the advantage of having this radar-based precipitation estimates. And we combine them with other data sets like rain gauges, other sources of privately owned radars, privately measured rainfall amounts, volunteer-based rainfall amounts, and then they combine all of them. They come up with a product which is reliable, and they provide that precipitation data to regional forecasting centers, and the regional forecasting centers run their simulation models to quickly come up with numbers, especially the stage thresholds, to give warnings to people about flash floods, and then any type of impending flooding which might happen in the next 2-3 hours. That kind of information is available. Okay. Any other questions?
The map which you have shown for stream flow, is it a
Yeah.
real-time or predicted one?
This one is predicted by the one.
Website one, sir. Website. Real-time.
This one.
This one.
This one is the actual values, actually.
Actual values.
Because these are stream flow conditions. So what they, in US, the discharge values are not calculated. They come as stage values. So the stage values are coming to the regional centers, and the regional centers will project the stage values, and those stage values are converted into discharge, and then they convert to the ranking based on percentiles, and then they color code them. So that will give us generally what happened in different areas.
So that means all the gauge stations, they are connected through satellites, which transfer immediately the stage values to a nearby center.
Yes, yes. So all of them are by, all the sites are by telemetry, so they are connected by satellite. So the regional processing centers will immediately get the stage values. So sometimes what they do is they provide the provisional data also. For example, if I click on surface water, they will give you the current conditions, and you can go and check each of these sites. For example, let's see. If I go and hit the daily values, or sorry, daily data, if you click the daily data, you can actually go and look at the provisional data that is available. May not be real time, but at least for the last 4 or 5 days, you already have the provisional data. Now, that provisional data doesn't mean that it is a confirmed value, because they are still going through the process of checking, applying the right discharge rating curve, which connects the stage and the discharge. So they apply the right curve and then get the values for the discharge. But the current conditions are purely based on the information they are getting about the stage, and that is translated to either rank from the stages or from the discharge values they are calculating. So, for example, if you see here in the streamflow data I have provided, that will also have a every discharge will have a stage value associated with that. So that way you can see, you can actually develop a stage versus discharge relationship based on that information. So for example, let me go here and show you. So this is the data. So this is how there's a station number, and then discharge feet. Of course, we measure in feet cube per second, or at least reported feet cube per second. The stage is provided, that is the value of the water height above a specific datum, and then we can always convert into meters. So this relationship is given to us automatically by the agency anytime you are looking for the data set. So. But I didn't download after 2022 February 15th, but you can get the data until yesterday. But some of this data are not, they will put a flag called P, that is provisional data. Okay, good. Any other questions based on the lecture today? Any questions on converting Z value to the rainfall values, bias corrections, mean field bias, ground truth? Because these are the very important things you need to consider if you are into flood modeling or development of or evaluation of distributed hydrologic modeling for your flood forecasting applications and so on.
Sir, there is a question in chat box. Some of the gauge sites in USGS are inactive now and only have past 2-3 years record. Are these sites gauged only for specific projects and become inactive now, or what may be the reason?
Okay, so that's a very good question. So we have some sites which are discontinued, either for lack of funds, because even in United States, there are some states do not have enough funding, so or they might feel like we don't need this one, or it was replaced by another upstream streamflow gauging station, or a streamflow gauging station have become inactive because of the upstream development or channel cross-section issues or other issues. So that station is abandoned for a number of reasons. So that is basically inactive. Now, that happens. Sometimes maybe there was a project that ended and they remove it. The third one is lack of funds. And these are the reasons why we may not have some sites which are useful for any purposes. So in that case, if we are missing stream flow at a particular site, which we want, either we have to do regional frequency analysis, which I will talk about it tomorrow, or we can do area-based disaggregation, which might be not the best, or we could use some data-driven approaches to reconstruct the historical stream flows if we really need that. And in many cases, if the watershed has not shown any land use changes, so for example, sometimes they will have a gauging station here, they might have a gauging station here. This was discontinued, so we might use some area-based analysis, or some kind of data-driven model, or some kind of frequency analysis to estimate or reconstruct those values for our project, if at all it is needed. But it so happens sometimes we remove sites. We also used to have more than 3,000 watersheds which are pristine. We call it as virgin watersheds, where we were monitoring long-term data. So right now we have around 1,500. I would say not 1,500. We have around 1,250 sites that are pristine watersheds that are available in United States, where you can download the data, and that data is mainly beneficial for climate variability and climate change studies, because these sites come from least anthropogenic affected areas classified by the United States Geological Survey. They do the basic tests to make sure that these watersheds are not affected by any urban growth or any development at all, least anthropogenic activity, and they classify them as the pristine watersheds, and they are part of the hydroclimatic data network. It's called HCDN. These are available for download, and some of them have data ranging from almost 100 years, so 1900, more than 120 years in some cases, but basic length is around 80 years, which might be extremely beneficial for climate change and variability studies. So I would recommend, if you are doing any climate change or climate variability studies, look for sites which are virgin, which are not disturbed by any human activity, and then look for any climate change signals, so that it's much easier that way to attach attribution to those changes than opposed to in places where you have a lot of human interference that can lead to confusing signals, whether it is anthropogenic or the natural climate signal. And separation of anthropogenic and natural climate signals is sometimes extremely difficult in some cases.
Sir, okay. But is this data freely downloadable, or we have to pay for it?
Every single data from this website is free if you are able to access the website. Okay. So for example, if you want to get a daily data right now, you can click on daily data, and then you can select hydrological region or a state. I click on state and territory, so submit, and then I go ahead and select Florida because I'm going to get one of the sites in Florida, and then I go down, and these are all this data is available. Some of them may not be for long term, but some of them, they also have some water quality data, meteorological data, but USGS is mainly the holder of the stream flow data. So you go down, way down, and then you submit, and then what it does is it gives you all the sites in Florida which has data, and they have a unique number. So you can go ahead, for example, I have St. Mary's River at McClenny. This is the one. There should be another one. St. Mary's River. St. Mary's River near McClenny. This is the one I'm using today. So you double click on that. You will have the information about the current discharge conditions. For example, this is May, and you can see. And then you can actually see that the discharge may be available from 1926. So that is the daily discharge data which is available. So you can actually download the data, and then once you have the data, so for example, I can click from 2008 to 2022, and then I can just get only these two information, that is discharge and stage height. So go click and go. Oh, sorry. I click the graph. I need to get tab separated. So I just go hit, and then I get this data. I can copy that. So you see the sign A means approved. And then when you go down, you will see the end values as P, that is provisional. Okay. So that means you can actually get the daily data available for you for your analysis. And that can range from 2008, or if you're interested from 1930 onwards, and then you hit go, and then it automatically calculates. So right now I'm in Italy, and I'm able to download the data. So does that answer your question, sir?
Yes, sir.
Yeah. So yeah. So in this case, what I'm suggesting is that if you are interested in climate change signal, look for those remote sites where I don't know if India is maintaining any of these sites which are part of the network. But United States used to have around 3,000 discharge sites. But what happened was, over the time, these sites have become either developed or they discontinue the discharge stations in those locations, so they miss those data. But we still have around 1,300 sites available, and I think I would say that I also learned that some of the students here are working on some data between India and Pakistan, the border rivers, and they are looking at water sharing issues, or they are looking at trench and other things. So if somebody in Italy may be able to get it, you should be able to get those data for India also. So that's my point. Okay, good. Any other issues? Any other questions?
One participant has asked, in relationship of Z is equal to A into R raised to B, whether it is necessary to consider the error term due to the presence of random or systematic error in the reflectivity values.
Okay. Yes. So basically, Z equals AR to the power B. That is our power relationship. This is based on the drop size distribution, the integration of the rainfall amount in a portion of the atmosphere, and the reflected values of the reflectivity. So this is much simplified, and there is huge calculation behind that. Now, the antenna or the radar instrument will have some systematic errors and some random errors, definitely. But typically, the agency which is providing the Z values, that is the reflectivity values, they try to minimize these two, right? They try to minimize these two. The rest, whatever are coming through in the form of errors within a Z, are there. Nobody can help, because these are the final values provided by the government agencies. They have done their due processing, they did filtering, they removed the echoes, they removed the background noise, they removed any type of errors they perceive which might be coming from the malfunction of the instrument, any errors and so on. So they would definitely check these values before they post it. And unless they are confident, they will not provide them as a product to the public. Now, whatever small amount of systematic and random errors that are left, we can only correct them by what we call the ground truth, that is rain gauges. So we have to do, irrespective of whatever ZR relationship we use, we have to do bias correction. So without bias correction, we cannot say that our data is ready for use in any modeling purposes. The interesting study would be in India is that the efficacy of different radars, for example, if you have a radar in Gujarat or Ahmedabad or someplace or Chennai or Delhi, it would be interesting to see how well they are able to capture the rainfalls with and without bias correction, and what is their accuracy, and are they really good for bias correction, what are they really good for any short-term predictions for flood forecasting, are they good for any hydrologic modeling, are they good for any design modeling, in the sense that hydrologic design for lump models, for example, if you just want to use one value at 24-hour maximum, is this radar giving reasonably good value for a location where there are no rain gauges, or something like that. Those kind of studies can be very beneficial, because now the radar data is slowly getting available to public, or at least installation-wise they are installing. So if you can get hold of some reflectivity values, at least you can, master student can work on evaluation of the reflectivities and biases for some regions in India, and that can be a beneficial study for both the student as well as the person, the agency which is providing the reflectivity data. Yes, the small amount of systematic and random errors will always remain, because the agency can only correct so much. The final step is the user, and it depends on what is the rain gauge density you have. If you have a lot of rain gauges in your area, then your bias corrections will be much better than if you have less number of rain gauges. That is one thing. The bias corrections will be much better if your quality of rain gauge data is good. That means you are having reliable rain gauge data where it is being quality assured and quality controlled. Sometimes if the rain gauge data is not available in your area, maybe you can use the global products to do the corrections, because now the global products are available at 0.25 degrees. That's too large, of course, but in the absence of that, there are some GPCC data sets. There are data sets produced by Germany for the global level, or you can use IMD gridded data products, which I have used in one of the studies. So you can use IMD data sets to see how well your reflectivity values are capturing in the past. If you have, let's say, past year's reflectivity values, you can actually check how well the IMD gridded data product is comparing with the available radar-based precipitation estimates which you are generating. And of course, if you have rain gauges in that area, you can also do some bias correction of the reflectivity-based rainfall estimates, and then check how well you are doing with respect to the gridded IMD data. You can do that. Good. Any other questions?
Yes, sir. There is one more question. Abdul Salim is asking, are lump models good for large ungauged basing compared to distributed models?
Okay. You do have large ungauged basins. That's what you said. There are ungauged basins, right?
Yes. Are lump models good for large ungauged basins compared to distributed basins?
Okay. So if there is a similar basin which has a nice distributed output by some luck or whatever, or it has some lot of rain gauges, definitely this one can be only useful for a lump model. Now, lump models is also difficult because you're saying ungauged. So when you're saying ungauged, there is no way to estimate the design flood in that area. So either you have to use some historical information or watershed characteristics to generate a 100-year peak discharge, or you have to use a regional frequency analysis. That means you have to use the nearby gauged catchments, gauged basements let's say A, B, C has some values, then you can infer what is happening in ungauged basin here. So definitely, if you are lucky to have some rain gauges which is gauged, and if you are able to get either IMD products or radar based products, definitely this is much better for distributed modeling applications. Whereas this one in the lumped model, definitely you cannot apply distributed hydrologic modeling because there's no way you can generate those gridded precipitation data. The best way you could do is, come up with some single value of flood value or single value of rainfall in that area, and then apply for lumped model. So this can be more approximate values of your flood estimation. This will be more accurate because you are having both rain gauges as well as gridded precipitation data for checking, for ground truth checking, as well as bias corrections. I hope that answers the question.
Yes, sir.
Yeah, so there is a huge amount of literature on ungauged basins. There is also a committee under IHR, it's called PUB, Prediction in Ungauged Basins. So if you want to refer to that literature, that might be very useful. It's easy to remember. The acronym is PUB, P-U-B, Prediction in Ungauged Basins. So that is the most difficult part. Now, what people are doing is that they are relying on satellite-based products. For example, previously we used to rely on TRMM, the Tropical Rainfall Monitoring Mission. Now we are relying on GPM, which has started in 2016. So we could use the satellite-based estimates. Unfortunately, if there are no rain gauges, even satellite-based estimates should require some kind of bias correction. But if, let's say, for example, we're looking at a basin here, and if there are rain gauges here, rain gauges here, rain gauges here, so the satellite-based products can be adjusted based on these rain gauges. So that means they can be bias corrected. So you bias correct the satellite-based products, and then since they are bias corrected, you can have some confidence in application of satellite-based products in this ungauged basin. So that is one way of doing it. So that means we are going through the route of precipitation to discharge. But you can also go directly to discharge by regional analysis. Okay, so that is also possible. Good. Any other questions? Okay, I would like to hear something no, so that I can move on to the next step.
Yes, sir. Next step.
Okay, good. So so we go to the next step. Basically, in the tutorial, I wanted to do a few things. Let me go to the one. Let me go here. Okay, tutorial day one. So I'm assuming that I'm not sure if somebody said, I think good number of people said they can do optimization. So I'm going to use some kind of optimization methods for estimation of missing rainfall data. Now, let me go through here. Okay, so missing rainfall data is a common feature, including a common problem, I would say, in United States and everywhere else. So approximately 20% of the data is either missing or anomalous or some kind of problems. So that happens very often because of number of issues. Either rain gauges are having issues, overestimation, underestimation, malfunctions, and all those things. So missing data at a resolution which is important for us, either for lump modeling or distributed modeling, is very critical. So we need to have some kind of method to estimate missing values. So that's the first exercise where I have provided some data sets. If you go here, I have provided precipitation data for your spatial interpolation. Okay, so these are some 15 sites in a temperate region in Kentucky. So it's not tropical region like Florida, or it's not or arid region on the west. This is a temperate region. Okay. Now, if you see here, these are daily data. Obviously, you can see the zero values. So if I take these values, there are around 8,000 values. So approximately 20 years of data is here. So one of the quick things we can do is, first of all, check if there's any persistence in our temporal data. This is daily data, so I'm just using MATLAB. But you can also use a software called or online software if you are experimenting. For example, www.vesa.net. This is a free statistical forecasting software website. Now, this one has all the statistical measures, correlations, visual analysis aids, as well as hypothesis testing, regression fitting, and everything. The advantage with that is that this uses the R software in the background, and anytime you are requesting something, it automatically does the calculations for you and then provides you the results. Okay, so if I go here, descriptive statistics, you have all those things calculated. You should also have, for example, autocorrelation function, which is the check of persistence. Okay, so let me delete this data. I can also do it in MATLAB, but I'm just trying to show you this website. So I'm pasting the daily data here. Okay, and then I'm going to say compute. So based on your understanding, is everybody okay with the word persistence or autocorrelation? Anybody has any question about that? If you have any question, please say yes, so that I will explain. It will be a benefit for the whole group. Otherwise, I will move on. Anybody wants to say yes?
Somebody is asking, what is persistence, sir?
Okay, persistence, yes. So typically what happens is that let's take a daily stream flow, or if you look at your hydrograph, right? This is your hydrograph. So what happens? This is your previous day flow, next day flow, previous day flow, next day flow, and so on. So at every interval, you are having the flow value. So a persistence is something, the property of a time series, that a high value follows a high value, a low value follows a low value, right? So for example, the ups and downs, right? So in this case, for example, if I have a linear line, high value follows high values follow high values, and so on. So basically, the persistence of a linear line is very high, okay? Whereas the persistence of a hydrograph is also very high because the current value has a strong dependence on the next value. That is called persistence, okay? So if you remember correlation is between two quantities. Autocorrelation is the correlation onto itself, but by different lags, okay? So for example, if I go and take this, I just took the precipitation data, okay? So if you look at the precipitation data, this is your precipitation data. So let's see if we can insert a small graphics of that. Even if you know the concept, please talk, so that it'll be interesting to see your feedback and being part of this whole lesson or even lecture also. Please make sure that you indulge in the lectures. So typically what happens, rainfall happens in the form of pulses. So that means there are some zero values, and there are some pulses of rainfall. Okay, these are in millimeters, by the way. So you can see that there are pulses. So rainfall, because of those disjoint, unconnected pulses, they don't have a lot of persistence. That means the persistence of daily rainfall is almost zero. So it is completely random. That means just because it rained today doesn't mean it will rain tomorrow, or just because there's no rain today, it will not be no rain tomorrow. So the persistence will be very low. So that will be reflected in our graph now. If I compute the persistence or autocorrelation using that VESA software, it'll give you a nice plot here. You'll see here. So if there's no persistence, the values will immediately fall below this statistically significant line. These are the two statistically significant lines. So most of the values will fall down. So that indicates that there is no persistence at all. That means the previous value will not help me to say anything about the next day's value or next value. Okay. Now you might say, what is this one here? That is the same series autocorrelate or correlated against itself. That will be 1 because it's the same series. So that is zero lag. Then what you do is you lag the values. For example, if you go here, let me go to the precipitation data here. So this is my data. So I copy and then I lag it by one day. Then I lag it by another day. Something is selected somewhere. Cannot select this. Okay, so basically what we are doing is we are lagging one value after the other by 1 day. For example, these are the stages. So I take this and then I copy and then I put it here. Lag 1. Of course, sorry, I need to paste special because those are converted to meters. So that's lag 1. Then lag 2. Then lag 3. So what we are seeing is here, I am taking the same time series, but I'm lagging by one value. These are called lags. So when you look at your autocorrelogram, these are the lags. So what you see here, does this say persistence or no persistence? Anyone from the group? If you're there, please use your microphone and tell me. Based on this graph, do you see persistence in our daily rainfall or not? You can be wrong, just say it.
Few answers are there, sir, in chat box. No.
Yes. So please, guys, use your microphone so that it is nice to communicate. Okay. Yes, there is no persistence because the autocorrelation values at different lags are within the statistically significant values of no autocorrelation. So that means using the previous value, I cannot estimate the next value. So that means the temporal interpolation of precipitation data is completely out of the question. Okay, so let's take the discharge values. I'm just going to take feet, or doesn't matter whether I take meter or, you know. So I take these values. These are my discharge values. So what happens if I take discharge values? Do you think there will be high persistence or no persistence at all? Before I click compute, I want to answer.
Slight persistence will be there, sir.
Definitely there will be persistence because high event follows high events, low event follows low events. So let me compute the persistence. You see that? Very strong persistent at lag 1, lag 2, lag 3, lag 4. So it's slowly going down. And then, of course, it raises a little bit. That indicates some kind of slightly stronger persistent at step 10. or time interval 10, and then it goes back down, slowly going down. So sometimes if you have other time series, it strongly goes down like this, and then that indicates that we can use the previous value to estimate the next value. That indicates that strong persistence. Okay, so for example, this is your hydrograph. Let me go ahead and get my stage values. I see some holes in the stage values for some reason. Okay, let me pick up from here. These are in meters, the stage values. Okay, copy. I'm just going to paste it in a separate page because they are converted values to units. So I copy them there, paste Spatial, and then I copy again, and I go to my, this time I'll go to MATLAB, which is easier. So D is equal to, I put the values there, then I close the parenthesis. So now there are 1,696 values of stage. So I can just plot the stage and show you how they look like. And this stage has a strong relationship with the discharge. As the discharge goes, sorry, as the stage goes up, discharge goes up. And sometimes there's a nonlinear relationship. So let me do an autocorrelation plot. The command is autocor in MATLAB. Okay, and then see what happens. See how strong is the persistence. It's almost like a 0.99 something. I can click on that and I can hear 0.96986. So very strong persistence for stage, and it is slowly going down. So that indicates that it's a heavily autocorrelated time series. That means today's stage, the water level, has a strong dependency on the previous stage, stage level. So now I have two time series. I'm going to ask a question. I have precipitation time series, which is a daily level, right? P at daily level and Q at daily level. This one has no persistence at all, no autocorrelation. And this one has strong persistence. Okay. So which one is good for spatial interpolation and which one is good for temporal interpolation?
Sir, P is good for spatial and Q is good for temporal interpolation.
Okay, who is this person? What is your name, sir?
Sir, Tushar Khanpoje.
Tushar Khanpoje. Okay, so you're right, because precipitation has no temporal interpolation. So that means previous value is not connected. So that means we cannot do any temporal interpolation. So let's say, for example, this is your precipitation time series. This is this value and a 0 value next day and 0 value next day, and then a very high value. So these two values are not connected. So I cannot use this value to interpolate what will happen here. There's no way I can do that in case of precipitation. Whereas temperature, for example, is a very smoothly varying continuous parameter. So if you take hourly temperatures, they'll be smoothly varying like that. So that means they have very high persistence. So if I have some missing observations like that, then I can do some kind of temporal interpolation. That is the advantage of that. So I can do a temporal interpolation because the persistence is very strong. So either I can build a linear model between these two. Right now, I can build a linear model. The linear model will be just joining both of them. It'll be a nice model. It still works because the temporal persistence is there in temperature data. Or I could do some kind of a non-linear model, which might introduce some error or may not be introducing any error. So temporal data for some climatic variables have high persistence that can help us in estimating missing values. Whereas precipitation data is one main problem. That's one of the reasons why there are so many studies for estimating missing precipitation values, because it's more complicated than temperature or stream flow, because temperature and stream flow have a strong persistence at different levels. Okay, so therefore tomorrow I'll show you that stream flow may not have persistence at monthly level. Stream flow may not have persistence at annual level. Stream flow may not have persistence at annual runoff levels. So depending upon the time scale, the persistence may change or the persistence may not be there. Now, why do you think there is persistence in our this data set? For example, stream flow data set, because it is because of the watershed response. When it rains, the watershed responds slowly, so the water moves towards the outlet, and then slowly we will see a hydrograph raising, and that slow raising of the hydrograph indicates that the persistence is very strong, and that really helps us in establishing the interpolation models. Now, let's go back to what we wanted to start thinking about. The idea of what we were thinking about is that how can we estimate missing values of precipitation? And trust me, you will encounter this problem in your research. Sometimes you need daily values of precipitation, and then you will have some problems in estimating the missing values. So of course there are so many methods we can implement. The simple method would be the inverse distance method, and I'm sure everybody is familiar with that one. So if you have, there are two issues in case of estimating missing values. So for example, this is your watershed, and then you have 1, 2, 3. If this is missing data, you can basically use the Euclidean distance. Let's say this is 2, this is 1, and 3. So this is 2, 1, and this distance is d2, 3. So you can actually use those distances, and then we can say that we can inverse those distances as our weights, right? The farther they are, the lower the weight is. So that's the whole idea of reciprocal distances. So once we have those reciprocal distances, then we can actually estimate the missing value theta m, and here it is theta 1 and it is theta 3. So we can actually estimate theta m is equal to 1 over d21 whole square, because sometimes we square the distances for renewed effect or strengthening the effect of the distance, multiplied by theta 1 plus 1 over d23 square multiplied by theta 3. That is, we are weighing the observations based on the inverse of the square of the distances. And then, of course, for calculating the reciprocal, we do the same thing, 1 over d21 square plus 1 over d23 square. So this is inverse distance method. The square is the effect where you strengthen the weight. You try to increase the strength of the weight. You can put 4, or you can put 6, you can put 8 also. The interesting thing is that this is most commonly used interpolation method for many hydrological variables, especially temperature and precipitation. Now, daily precipitation, yes, but sometimes daily precipitation may not be working very well using this kind of distance-based interpolation. Or it also depends on the climatic region. In some climatic regions, precipitation varies based on distance. So in that case, distance can be a surrogate for association. So you can estimate the missing values by inverse distance weighing method. It's called IDW. Okay, so that is most commonly used even for gridded data generation also. So the gridded data generation is something like this. So for example, you have rain gauges here, and you want to generate gridded data. So what you could do is you can define the whole region into a Cartesian grid of a specific resolution, and then for every centroid of your grid, you can use again inverse distance to estimate the value here. When it comes to the next value, again, you use those distances. So trust me, many well-known gridded products are also generated by what we call inverse distance weighing method. Okay? Any questions on that? Okay. I'm assuming there are no questions.
Sir,
Okay. Please ask.
Please go
hello,
ahead.
sir.
Ask. Yeah.
Yes, sir. Whether we can do spatial interpolation of daily temperature, sir?
That is very well, without any problem. Yes, you can do it, because that's the advantage of, it depends on what are you trying to daily maximum or minimum or average. Average works out very well because that's the, general central tendency value of the precipitation in a given day. That works out very well. The extrema, again, sometimes depends. But the strength of the the strength of the spatial interpolation depends on the density of your observations. The more observations you have, which we call them as control points, these are control points. So the more control points you have, the more appropriate the product is, that is spatially interpolated product. But there's no doubt you can do daily temperature interpolation, both spatial or temporal. We can do that. Now also you can generate a gridded product like this, which might be beneficial for your modeling exercise, either hydrologic simulation models or any other climatic models you can do. But provided you test how well you use your interpolation. Okay, so that means we have to test. Once we develop a model, we have to test how well our model is doing, and that requires you to do a number of steps. That means the first thing is that you keep away some points for your validation so that you can check how well you are doing. Good. Any other questions?
Yes, sir.
Another question is, sir, what is the minimum value of persistence to have in stream flow?
Okay, the minimum value of persistence, there is no minimum value, but if there is a strong persistence, let's say 0.8, 0.9 at different lags, for example, here we have the stage, so we can do a model for stages. So if you see here, this is the persistence is very high. So that means I can use probably these two values to predict the value. So let me write the simple model for that. For example, discharge at time t can be linked to discharge at time t minus 1 and time t minus 2 and so on. So I can decide how many previous discharge values I can use for prediction of my next value. So if the persistence is very strong for the first three values, when I say persistence, anything above 0.8 is reasonably very strong persistence. Anything less than 0.5 is not strong, strong persistence, so we may not be able to use it, or we might not be able to beneficially develop a forecasting model. But once it is more than 0.8, yes, it is. That is, the previous value has a strong dependence on the next value, so we can use in our model development. Now, this is a simple model. So the simple model can be a multiple linear regression. So W1 times Q T minus 1 plus W2 times Q T minus 2. So we can actually develop this model in Excel and then try to find out the best weights that can help us to develop this model. And that's what we can do today. If the time permits, we'll do it. Okay. So yes, we can do, but there's no minimum persistence that might come out of a particular time series. Some series will have very strong persistence, depending upon the size and the shape of the basin. You might have higher persistence at multiple lags, and some may not have that much. So when developing a time series forecasting models, dependence is very important. So in spatial interpolation and time series forecasting models, the dependence is important. But if you do a traditional statistics, the dependence is not a good thing. We need to have independence between the samples. That is what is important in traditional statistics. But when you're doing time series modeling, or when you're doing spatial interpolation, that's when the what you call the persistence matters. And in case of spatial interpolation, if you are looking at, let's say, this is your watershed and these are your rain gauges. If this is missing the data, at least some of these gauges should be related to this. If they are not related to that completely, then there's no way we can build a spatial interpolation model. So in case of a spatial interpolation model, the variable of interest is interconnected with other location measurements. So that means there is some kind of spatial dependence. If that dependence is not there, there's no way we can do even spatial interpolation also. First of all, temporal interpolation is gone out of the question because there's no persistence in the data. So we are finally get down to a point where we have a spatial interpolation that is possibility. So think about like this: you are sitting in a classroom, and then there are 3 students or 4 or 5 students like this. Now you have written 4 exams, 1, 2, 3, 4, and everybody has written 4 exams, 1, 2, 3, 4, 1, 2, 3, 4. So for some reason, your instructor has lost these 2 exams. So if you don't have a strong persistence, your instructor cannot use the first exam's value to predict what will happen in the second exam value to predict what will happen in the third exam. So you don't have temporal persistence. So we cannot use a temporal model to fill your points or grades. So then what we do, we try to see what is the relationship between this student and this student, between 1 and 1, 1 and 1, 4, sorry, 1 and 1 here, right? Here also, no, this is 1 and 1, sorry. And then 4 and 4. So if there is a strong relationship between the first exam of yours and first exam of another student, and fourth exam of yours and fourth exam of another student, 2 students, then I can use them for spatial interpolation. If even this is not possible, there's no link, all students are completely behaving randomly, which there is a possibility in a classroom, then I cannot do spatial interpolation. The only way I can reconstruct your marks is to give you 2 exams again. But luckily, in spatial interpolation, in case of hydroclimatic variables, for example, temperature, humidity, or other variables, evaporation, there is some kind of a natural dependency that is happening. That means we have a link between all these other control points, because the process is varying in a more smoother fashion over the region. Okay. Now, it would also help to have more denser network so that we can capture that spatial dependency very clearly. If there's a very sparse network, very few stations are there, even spatial interpolation can be a problematic thing, because we cannot confirm that what we are filling is the correct value or not. Okay, so the best way is to use other sources. For example, if you have radar or if you have satellite, use those sources to fill those values and then run it through a simulation model and see if you are getting reasonable results. If you're getting reasonable results, that means the filled values are correct. So for example, if this is your precipitation series, and this is the gap you have. So if you put that into your simulation model, hydrologic simulation model, then what happens is that you might have something like this. Okay, that gap, because of the zero rainfall, might show zero discharge. But in reality, there was some discharge. So what does that mean? That means whatever values you fill here, if they reflect reasonably well and then help you to achieve that simulation, then these values are reasonably okay. But that can be filled by a good spatial interpolation method. Okay, does that answer your question?
Yes, sir.
Okay, good. So please interrupt me if you have any other questions. So anyway, so now we found out that streamflow data can have good persistence that can help us in developing a nice temporal model, whereas we have clearly seen that precipitation data is a problematic thing. Now, the other thing we need to also check is that whether these stations are correlated or not. Okay, that means whether this one is correlated to this one is correlated to this one. So we can actually find out all kinds of correlations between this. We can develop what we call a correlation matrix, right? So just to find out correlation between these two, we can actually see if there's any correlation between these two. And visually we can check, or we can check using what we call the Pearson correlation coefficient. Right? So I'm just going to take these two data sets to see if there's any slightest level of correlation in MATLAB. So I'm just going to paste them there and then show you if there's any correlation between these two data sets. So if I use cor, that is the command correlation, Pearson correlation command, okay. So there's not much correlation between that station and this station. It's a possibility that this station may be far away from the station where we are looking at. So therefore, the correlation is very small. So we can use correlation also as some kind of a weight to do our estimation. Okay. So now let's say, for example, this is our data set. Okay. And I want to estimate missing values at station 15. Okay. So what I will do is, first of all, I'm not going to randomize the data, which I will tell you why we have to randomize the data. So if I have this data, I will just highlight them with yellow. And of course, typically, if you are developing a model, what is the percentage of calibration and validation generally? Anyone?
75-25, sir.
75-25 or 70-30 or 60-40. Nobody has any perfect perfect rule for that. The only thing we need to make sure is that if you are taking a chronological set of observations, let's say this is let's say 1970 to 2022. If you're taking observations like this, you better be careful that if you're taking this as a calibration data and this as a validation data, let's say 70 and 30%, make sure that the patterns which appear in this one also appear in your validation data. Okay, so that's what we call as selecting representative data when you're doing model development. Okay, now this is one way of breaking down your entire series into calibration validation series. There's also other mechanisms by which you can break the data into calibration validation data sets, which can be called as k-fold validation, and there are a number of things which I will discuss, but the simplest one is you arbitrarily fixing a percentage of data for your calibration, and then the rest is fixed as validation. So that is one way of looking at your calibration validation data. There is a good chance that the patterns which appear in this first part of the data set may not appear in the second part. So in that case, the model is developed based on the calibration data, but the validation data has not seen such patterns. So in that case, there is a possibility that the validation data may not be very good. So you may not be able to get the better performance when we are working with the validation data. So you have to be careful. Maybe there's another way of randomizing the entire data set. So how do we randomize this data set? Let us say we don't want to take the first 70% and the last 30% as our validation. So for example, I will use a different color to color code the last 2000 values as my validation. So that's one way of doing it. So if you want to randomize this data quickly in Excel or in MATLAB or any other place, what would you do? So that the representative values are represented on both sides, that means calibration and validation side. Okay, if you want to do that, what will you do? Anyone has any ideas? So the blue is validation, the yellow is calibration. Yellow is calibration, blue is validation. 70%, 30% approximately. So I may be falling into the danger of having this patterns which are there in calibration may not be repeated in validation, or vice versa. So there is a possibility that my model may not be doing very well. There's a very good possibility. So any recommendations are to randomize this data so that I mix this whole data but still take some 70% out of it and 30% out of as calibration and validation. Anyone? Just as some kind of a technique.
Sir, we'll fix the minimum and maximum values and find the ratio.
We fix the minimum and maximum values.
From 0 to 1 and then
0 to 1. Okay, minimum and max. Okay, so you're basically asking to sort it, you mean? Sort the data?
no, sir, like we'll fix 0 as the minimum value would be 0, so 0 as 0 and the maximum value as 1, and then we will arrive at the ratios of these values. For example, 18.28 will have a ratio.
Okay. So you're basically saying standardize them by dividing
yes,
by the largest value, right? That's what you're saying.
Sir. Yes, sir.
Okay. So instead of standardizing, maybe that's a roundabout way or may not work. Let me do a simple way. I generate a uniform random number called rand. Okay. So I generate the uniform random number, and I have this uniform random number generated until the end of the time series in this column, right? Thought I could do that. I'm not a good Excel person, so I think I need to drag it. Okay. So basically what I'm doing is I'm generating a random number which will be between 0 and 1. So I'm using what we call pseudo random numbers, because computer cannot generate real random numbers. These are pseudo random numbers, but that is fine. They will do the job for me. So I basically generated random numbers, and because Excel changes every time I change the cell, I'm going to copy it and then paste it again as special so that the values will remain there. Okay, so everybody clear what I have done? I basically generated random numbers. So now what I do is, actually these two first columns are not useful, so first two rows are not beneficial for the time being. I'm just going to remove them. So this is my actual data. I generated random numbers. So what I do is I select all of them. I select all of them, right? And then I go to data and then I sort them. Okay, sort by the random number column, Q. Now Why am I selecting all of them? So that the temporal order across the stations is not disturbed. So it means the rows will remain same, but they get shuffled. That's it. So I say, okay. So now what happened? Everything is now shuffled, but these values are the same. Same in the sense that these values are one value for that particular time interval. They are okay for one time interval. But this may be January 1st, 1970. The next one is December 31st, 2001. So that is the randomization. So once I do the randomization, then I can decide I will use the first 70%. Now I can color code. Okay. Now I can color code up to 5,000 or so, right? Approximately. This is my calibration data. That's it. That's my calibration data. And the validation data is below it. So is that clear to all of you what I have done? Will you be able to do it? So the rest is my validation data. So I have to always keep the validation data so that I know my model can be tested using the validation. So this is how we basically randomize a set of values so that we can mix and match so that the patterns, what is learned in the calibration data, may also appear in the validation data so that we are okay when we are developing the model. If you are developing the model based on a chronological time series, especially in time series forecasting, and if you don't randomize, there is a possibility that the model will be learning only the first part of the data set and the second part of the data set. So why it is dangerous? For example, maybe the first part of the data set up to, let us say, 2000 may not have gone through any land use change, but suddenly after 2000, a lot of land use changes have happened here. So that means we are training on some different data set and we are testing on some different data set. It's like when you take your driver's test with your car, you're practicing on some roads, and you're only practicing on some roads which you are not familiar, which you are familiar with. Okay, maybe in your subdivision, maybe in your area. But then when you go to the test, the inspector, the driving inspector, will take you to different areas which are highly complicated than your residential area. So in that case, you will fail the test. So therefore, whenever you are learning something from the data, you have to learn from all the data set which is representative of the model encountering those data sets. For example, model might encounter some data from this side, and model may encounter from this side also. So therefore, you should be training your model on both the data sets. But again, the randomness is important. So in that case, how do you do the randomness? You try to get the data to randomize for you, and then select the calibration and validation data. So the other one, somebody was suggesting, that is more of a standardization. Standardization is required in some cases, but this is randomization. Okay, any questions on that?
Hello, sir.
Yeah.
Sir, but for time series analysis, if we randomize the data, so does the sequence get disturbed by that, or it is
That's an
okay?
excellent question. That is an excellent question. Yes, the time series analysis randomization will not work. Okay, so in that case, we have to come up with a different method so that the representative values are available in the system. Okay, so in that case, this is for spatial interpolation, right? So for time series forecasting models, the best way to do is that you take the data chunks. So for example, you take this chunk as your calibration and you leave another set of for validation. Then you take another chunk, then you take another chunk, and then another chunk for validation. So basically what you are doing is you are taking blocks of data so that the order is preserved, and when you develop models based on these blocks combined together, the order can be preserved, because, for example, let's say you are developing a time series forecasting model QT minus 1 and QT as two columns, and then QT plus 1 is your next value. So from this block, you can always arrange them in this order. Then you can go here, and then you can also arrange them like this. So am I making sense? Is that a feasible option?
Yes, sir. That will preserve that sequence to
Yeah.
some extent.
So yeah, to good extent, to without any problem, you can preserve and train the because all it needs is the training pairs, right? Input output pairs. So these are the two input pairs which are connected to this one. So as long as you are able to get two previous values from this block. So let's say, for example, you are here. You cannot be here. You cannot use two values from the validation. You cannot use it. So when you start here, you have to start from the third value in this block, and then use the two values, and then you can arrange like this, and then you can develop your model. So that way, what you're doing is, if a basin has gone through some kind of changes, you are capturing through your models. Does that help you, right?
Yes, sir. Thank you.
Okay. Any other questions? Okay. So the best way to randomize is this way. But if you still want to know the order before randomization, you could have put the numbers here, so that again you can get back to the original numbers after you have finished your calibration, validation, and checking your model and everything. You could have done that by just putting a serial number next to it, for example, 1, 2, 3, or if you have retained the date next to the data set, so you'll still have the the dates available to you. Okay, so now this is your randomized data set, so I don't need random numbers anymore. I can delete that, and I will create another. Okay, so these are my 15 stations. So assuming that this site is missing data. Okay, I'm going to give a different color to this. So assuming that this site is missing data, so what I'm going to do is use all these observations to estimate the missing value. Okay, is that clear to everyone? And first I will develop the model based on the yellow part, that is the calibration data. I'm going to give one gap here so that we appreciate what is happening. And so this is my end of the calibration. And the below is the validation. Okay, is that clear to everyone? Okay, any questions? Good.
Yes, sir.
Okay, so I need some confirmation. Okay, so the missing value theta m is equal to, we can develop something like this model. Okay, the missing value is a weighted combination of all the other observations. Okay, sigma of I equals 1 to n minus 1. N is the total number of stations. N is equal to total number of stations. Oh, something is going on with my pen. N is the total number of stations. Okay, so that is available. And then, so how do I get the best values of? How do I get the best values of this one? Any thought? Right? So you're fitting a kind of some simple linear regression, multiple linear regression. That is what you are fitting, right? Agreed? You're fitting a multiple linear regression. So that's why I asked you if you're familiar with the optimization, so that we can look into this thing. So any clue on how do we go about this so that we can get the best weights? Any idea? Anyone just want to show me some clue? No?
No one, sir.
Okay, so
Or we can
basically,
try with correlation, as you told.
no, we are going to develop some weights and we are going to optimize the weights. So what we are going to do is, let's say, 7,000 values are there, right? 5,000 values are there in calibration. So we will develop a small formulation called optimization formulation, minimize I equals 1 to 5,000. Let's say approximately, I'm just putting 5,000 values. Observed minus estimated. I put a hat on that, okay? And then I square it because I want the differences to be minimized. So this is my objective function. And then subject to constraints, if I have to have constraints. In this case, I want the estimation. How do I get the estimation? Is equal to, the estimation is nothing but Wi theta I summation of I equals 1 to n minus 1. That's it. So basically what I'm doing, I'm estimating, I'm trying to estimate the value, and then once I get the estimate, I will minimize the square of the values using my optimization approach. So once I optimize this whole objective function and minimize this whole value, the total quantity of that value, I will get the best weights possible. Okay? Is that clear to everyone? Good?
Yes, sir.
Okay. So all we have to do is, let's use the first row for our initialization of our weights. So I'll put a completely different color. Okay. So I'll put initially all the weights to be equal to 1. Okay. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. So of course the last one will not have any weight because we are estimating for the last column. So remember, last column is for estimation, not for anything else. Okay, we keep it that way. Okay, the last column, oops. Put the black color. Okay, the last column is for estimation. It will not have any weights. Sorry, last column is observed value for a station, last station. Okay, so now I have to write my estimate here. So I'll put estimate. My estimate is nothing but the product of this weight times this, plus this weight times this weight times this weight times this weight times this, and so on. So there's a command called sum product in Excel. So I can do this, where I can select all these weights, and then I will select all this thing, and then I can close the bracket. But then of course I have to use a $sign in front of A and 1 so that it always picks up the same value, and then it does the sum product. So first one is 0, we all know, because all the values are 0, the weights are 1. So what I'll do is I will drag it till the end of my calibration period. Is that clear to everyone? Any questions while I'm doing it, you can ask. Oops, sorry. Okay, let me estimate for the whole thing, so that because I want the estimate for the entire series, even though I'll only use the calibration data for optimization. Okay, everybody okay on that? Let me go and ignore the error. So that is my estimate. Any questions?
No question, sir.
Yeah, okay. So let me estimate the error. What is the error? Error is nothing but observed minus estimated. And then I cannot leave like that because there will be negatives and positives. So I'm going to square the error. I can use mean absolute error. I can use root mean squared error. I can do all kinds of things. But I'm going to calculate the error. But of course, I don't need the error until that point, but let it be okay. But I will stop the summation only up to the point where I am doing the calibration. Sorry. So the calibration is only up to this point. So therefore, I will estimate the summation of the error. I hope people are following. Okay. And then I'll go ahead and get my summation of my errors. Now I'm doing this Excel because then you could do using a sophisticated mathematical optimization approach like MATLAB or other types of solvers which are out there. But Excel is something which is reasonably a good solver, which is available to every one of you. You can do your own optimization of spatial interpolation and so on. So I sum up all the errors. So that's my error. Agreed? So that means I have some estimate and I have the observed value. The difference is the squared and the summation is the total error. Now that's the error. So I need to minimize that. So how do I minimize that? I can use solver. So go to file, go to options and get your solver, add in, go. Oops, sorry, it's already there, but I'm just showing for people who are not used to solver. So you say solver there, add in, go, and then here add that solver, add in, and then say okay. And when you do that, typically the solver appears under data, and you see solver. So solver is a nonlinear optimization solver. It also has linear optimization and so on. So set the objective. The objective is to minimize that error, right? So I'm going to select that cell which has the objective function. That is error. That's the cell. And by changing the coefficients, what are the coefficients? All of them are the coefficients. And we don't have any constraints. If you want to put constraints, upper limit and lower limit on your weight values, you can do, but I just leave it freely. And you see set objective to minimize, so change it to minimization. And then you say solve. Of course, you can use linear or non-linear. Just use non-linear, it doesn't matter. And after some time, you will see the best solution appearing for you, because if you see at the bottom, the objective function is getting minimized. And finally, you got the solution. Okay. So what does that tell you? That tells you that these are the weights it would like to assign. And it's saying that I don't need any weights for these 3 stations, but that means these stations are obviously not useful to me. That's why it is putting 0 values there. So that means the optimization is already selecting the control points. Out of 14 stations, it is selecting 1, 2, 3, 4, 5, 6, 7, 8. Is that clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir. So 8 control points are selected, and it is throwing away the other ones, saying that unfortunately these stations are not helping me to improve my estimates, so I'm not going to use them. That's why it is assigning a 0 coefficient to it. Okay, now this is our estimate. Let us see how well we are doing with respect to estimate versus predicted value. Okay. Let's see if we are doing any good or not. I'm going to take some values and then I'm going to plot them. So I can plot them like this, like a time series plot. As you can see that there is some underestimation for values, which is definitely possible. The best ideal graph is to plot as a scatter plot. So this much scatter is possible because of the daily data. So as you can see that there is a overestimation. Whenever we have zero values, the interpolation is telling overestimation. Okay, so that is possible. But then we are estimating the missing values a lot of these missing values. But our main interest can be in both validation as well as calibration. So let me see how well we are doing with validation. So this is my validation data, 2000 values. Let's see, I may be overestimating, I may be underestimating. Okay, so this is how I'm doing, not bad. But of course, I have some issues. But this is a simple, what we call linear regression model for estimating missing values at a location using a simple spatial interpolation approach. Okay, now how well we are doing, of course, visually we are okay. There are some overestimation and underestimations possible. We can also calculate what we call the correlation coefficient, that is the Correl means the Pearson correlation coefficient. So I would say, where are we starting from our validation data? 5080, 84 or 85. So I will use 05885 to 07932, comma, and 25885 to 27932. So that's fine. So I'm getting a correlation coefficient of 0.8. So that indicates that my values, which I'm trying to estimate for the daily precipitation data, which I'm assuming them to be missing, and I'm using an optimization approach to estimate missing values, I'm doing reasonably well for a simple linear regression model. Okay, instead of using inverse distance method, which may not work out very well, I'm using some kind of an optimization approach. Here, I'm trying to minimize the, this is basically squared error. Okay, square. You can also use what you call root mean squared error. Optimize that. Or you can use mean absolute error, or you can use absolute error. So, or you can raise this one to a power 4 to magnify the errors, so that when you magnify the errors, of course, you will not use a what you call odd power, because that will result in negative and positive values. So this is how a simple spatial interpolation model can be developed by optimization approach, where we are using the control points which are available for us and then assigning a weight, and let the optimization decide what is the best weight it can assign based on the data set. The more the data set you have, the better model you can develop using the optimization approach, and then finally estimate the missing values. Okay, so what time is it, by the way?
Thank you, sir. It's already 9 o'clock in India, and
Okay.
there are few students, girl students, who have to go to hostel, back to hostel.
No. Yeah, sorry. So we'll stop here.
No need to sorry, sir. It's a very good presentation.
Yeah.
Very nice. And I think we'll stop here for today.
Yeah, tomorrow we have the tutorial session also. I'll continue some other problems tomorrow.
Yeah,
okay?
sir.
No.
We can continue from here. There is only one question left, sir. That how do we identify the pattern in data during calibration and validation? Is there any statistical indices can show that pattern is similar or different in those periods? I think we'll take this question in next class.